Okay, welcome to session number 8. And this is on graph algorithms. And so this topic is going to be included just for the final exam, right? We will have homeworks 8, 9, and 10. And these homeworks will be due on, I think, around the 3rd week of May, right? So these topics on these homeworks are considered for the final exam, right? So now you have all the topics and all the sessions and all the homeworks and all the exercises for the midterm exam, right? That is going to be held on the 28th of April. Any questions about previous topics? We had a tutoring session on last Friday. The recording is there in the Google Drive. Also, if you want to check it out. And I think what you should do is just, prepare homeworks 5, 6, and 7 that you should submit on the 22nd of April. Right after that, in that week, I'm going to give you the solutions of all homeworks. And also, at some point, I'm going to give you a sample exam, right? To be prepared for the exam that we are going to have on Monday, 28th. Yes, Cesar.
Professor, I just have one question. For example, when we have two algorithms with the same, for example, with ON complexity, but when you calculate like the complexity, you have that for the first algorithm, it is 6n, and then for the other one it's 5n. We can say that the second algorithm is more efficient than the first one, or
Not really, not really. You just say that they have the same complexity and the variation is just the constant, but it doesn't matter at the end, right? The
okay,
important thing is the complexity of the algorithm, right?
okay, thank you. And I have a question about the homeworks. You just said that for the exam it's only until the seventh homework.
7th homework and 7th session, right?
Okay.
So this session, the session today, the today session is not coming in the midterm, right?
Okay.
So
Perfect. Thank you.
just be prepared for the first 7 sessions for the midterm exam. And also consider the 7 homeworks, right? And remember that the homeworks 5, 6, and 7, they should be uploaded by the 22nd, right, of April, right? Just after the Easter week. Remember that next week is Easter, and all activities in campus and tech in general are off. Okay, is that clear? So we don't have a lecture. We are gonna have a lecture in about 15 days, right? And probably we're gonna have special instructions for that because I have to travel abroad, and I'll give you some instructions on how we are going to hold that session in particular, right? And the idea also is to present the final project, right, in next week. But I'll give you the details later during this week, okay? So today we're going to talk about graphs, right? Graph algorithms, and today is not 8, it's 7. I just realized, so I make the proper change here, right? Okay, so let's so previous sessions, everything about you know, topics that are included in the midterm exam, right? From 1 to 7 sessions, from 1 to 7 homeworks, right? And this topic is a new one, is also a important one, but we are going to use it just for the final exam, right? So we're going to do a brief introduction of graphs, a search in graphs, and then algorithms for the minimum spanning tree, the shortest path, and the by connected components. I will mention the transitive closure algorithm and some uh, modeling, right, of graph algorithms for difficult problems. And we are gonna start talking about the NP problems, remember, that we did in the first session, right? In other graph problems also. So that those are the contents of today's session, right? So graphs. What do you understand by graph? By a graph? What is it? What is a graph? Especially in, you know, in mathematical, in a math context, also in computer science context. What is a graph? What do you have in a graph? Hmm?
Well, I think there are objects that are in some way connected between them. Well, there are two things. One is a set of objects, and the other one is a topology or a way to connect those objects by means of lines.
Right? These objects that you call usually, you know, in terms of the graph notation, usually they are called nodes or vertices, right? But you're right? The idea is, you know, I represent something at the end, right, with a graph, a relationship between nodes and in edges, arcs, right? And sometimes I can include weights, right, representing something, distance, cost, or you know, a factor there, right? But you're right. So this is what we are going to do, right? A graph is a representation. What can I represent in a graph? Many applications, many problems, right? There's you know, a large number of books about talking about graphs or using graphs or describing graphs for different applications and algorithms for that, right? And some problems are easy, some problems are not that easy, right? But the idea is, right, a graph is usually what I represent as I was telling you, you know, this connection between nodes through arcs or edges, right? And when I say a graph, it means that the connection, these arcs, are not directed, as in the case when I use a um, digraph. In this one, the idea is that the connections, the arcs, they have direction, right? They connect this node with this node in this way, but not necessarily the other way around. And in this one, it doesn't matter. I can connect this to here, to this one, or this to this one, and that is okay. So that is what is called an undirected graph. That is a graph, right? A digraph, you use direction in the edges, right? And what are they used for? Well, many applications, right? We use them here in computer science, you know, for connecting networks of computers. You have nodes, they are the computers, and you have different connections, right? In many applications in the web, right? We use a relationship between numbers, right? The web, many applications that use graphs, right? Sometimes I have simple graphs, right? Like this one, but sometimes I have complex graphs with complex connections, right? Representing, somehow with colors in the nodes, groups, or a clustering, right, of elements, et cetera, et cetera. So there are many, many applications on graphs, and that's the reason in computer science it's important, to understand the concept and to understand how we can use graphs for many different applications, right? So far, so good. Okay, so if we go to a more formal explanation of graphs, so I have a graph, right, which has a set of vertices and a set of edges, right? And then what is a subgraph? It's a graph G prime in which B prime is a subset of B and E prime is a subset of E. And it's also important that, the set E prime belongs, right, to the connection, the nodes in E prime, they are in B prime also, right? So that is a subgraph. It's just a segment of the graph, right, in which you take some nodes from the original graph, and then you have connections between that set of vertices B prime, right? Right. For example, if I have G1, this is the original graph, and this is a G2, which is a subgraph. So I select that, a number of nodes, and then corresponding edges connecting those nodes. So this is a subgraph, right? It's just a segment. So that is an easy concept, but that is important, right? And what is a complete graph? Normally, it's undirected graph with an edge between each pair of vertices, right? So for example, I have this one, and what is a complete graph? So I have connections, this and this, 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 right? That one, and that's it, right? So what is important here, right, in this case in particular, is to count, for example, the number of edges in a complete graph. What is the number here for this graph? What is the number of edges?
6.
6. And if you have an n complete graph, what is the number of edges that you have in the complete graph with n nodes? You have n nodes, right?
N
How
plus
many?
N plus n divided by 2.
N times what?
Okay.
I have
N
this one.
times n minus 1.
N minus 1, right? 1, 2, 3. 1, 2, 3. Right. So this is n times n minus 1 and divided by 2 because of what? What is the reason that I'm dividing by 2 here? I use this edge from here to here, and I use this edge from here to here, right? So that's the reason.
So because it's undirected, right?
It's undirected. That's correct. So I use one edge. I use it in both directions, right? From one node to the other and from this to the other, right? So that's the reason, but it counts just as a single edge, right? So this is the number of edges, right? If I have an algorithm that is going to traverse, all the edges that I have in the complete graph, so the complexity of the algorithm is going to be what? In which terms? Something like what? In what?
In a square?
In a square. Yeah. So there's a relationship, right? Between the problem that you have in a graph, the algorithm that you're going to use, and depending what the algorithm is doing, right, is going to relate to the number of edges in this case, right? And the number of edges is related to what? To the number of nodes or the size of the graph, we can say, right? So you relate all these terms that we have been revising, in the different sessions, right? Size of the problem and then complexity of the algorithm. In this case, is going to be related not only to the number of nodes, but to the number of edges, right? So is that clear? Yeah? Okay. And what is a path? From B to W in a graph, right? G is a sequence of edges, right? B0, which is the initial node, to B1, and then B1 to B2, and BK minus 1 to BK, right? In such a way that B is the initial node and BK is the last node from B to W, right? And the length of the path is K usually, right? So the number of edges that you traverse from B to W, right? A vertex V alone is considered to be a path of length 0 from B to itself, right? I can have this node here and say, well, the path is just, an arc pointing to itself, right? So for example, from here to here, this is B, this is W, and then I take the path, right? Can I have different paths from going from one node B to another node W? Of course I can, right? For example, here is another path, right? That I can use. It depends to what you want, right? The shortest path, which is an algorithm, right, for finding the distance between an origin and a destination, right? An undirected graph is connected, right? Is connected, if only and only if for each pair of vertices B and W, there is a path from B to W, right? For each pair. So you have, for example, this graph. Is this graph connected? Connected. Is this graph connected? Is my question, according to the definition here.
Yeah, everything is connected.
Everything is connected, right? You choose any pair and you find a path, right? This one and so on, right? So there's a path, right, from any V to W, so that is okay. So in other words, right, but for
I have a
example,
question. Are there algorithms to search if there is a path between two nodes?
that's right, yes. Of
Oh,
course,
okay.
yeah. And
Are
you
we
can
going to
imagine
see
what
them?
the algorithm is, right?
Well, I was thinking in A star, but I'm not sure.
Well, A star is not, well, it's uses, traversing path, you know, for going from one place, from one node to another, right? It's like going from the root in a tree, right, to a leaf. So you have a path there. How can I search for that? We will look for the algorithms a little bit later, but yeah, it is correct, right? So you have an algorithm for finding the path, right? Right. So what is a cycle in a graph? So let me just go back very quickly. So for example, if I have the graph, this graph, and I assume that there's no connection, right, between A and B, for example, there's no connection. So in the graph is still, you know, or contains 6 nodes, right? The graph is not connected, right? Should be should comply with the condition that for each pair of vertices you have a connection, right? A path that connects. If, for example, this one is not connected, so the whole graph is not going to be connected, right? Okay, so what is a cycle in a graph? What do you imagine that you have a graph, and then you have, in the first case, you have a directed graph, right? And you have a cycle is just a non-empty path such that the first and last vertices are identical, right? So I go from here and I come back there. So and for the directed graph, I traverse a path that has the direction, right? Between the nodes connected, and then I return to the same node, right? The first and last are the same node here, right? For an undirected graph, the definitions are the same, but there is another requirement that if any edge appears more than once, always appears with the same orientation, right? If I say I'm going from here to here, right? So that's the direction that I'm going to use, right? To say there is a cycle in the graph, right? I cannot say, well, I go and then come back here and then I want to come back over there. That is not, you know, complying with the condition, right? So that is a cycle, right? That is a cycle. If remember when we had you know, for example, a binary tree, can you find a cycle there?
No.
No, right? Correct. But if you have something like this or something like this, yeah, you have a graph in which you have a cycle, right? Somehow you have a cycle. So this is going to help me, you know, to define uh, aspects later, like for example, in this case, the definition of a tree, right? A connected component is a connected component of an undirected graph is a maximal connected subgraph of G. I have G here, and what I'm looking is a connected component. That connected means that I have pairs of nodes here and they are connected, but sometimes I can have in a graph G, I have several connected components. It means, you know, that elements here or vertices here are connected, vertices here are connected, and all vertices here are connected, but vertice, this, for example, and this one does not connect in the same way here. So this is what I'm telling, or I'm stating here with a connected component, right? And when I say that is maximal connected component, is a maximal subgraph that is connected between or inside a G graph, right? So this is a subgraph that is connected. right? So I have the whole graph here, and I have two connecting components. So this is just an example, okay? But there's no connection between any of these nodes here with any of these nodes there. Still, my graph is G, and I have two connected components here, okay? And then a tree is an undirected graph in which any two vertices are connected by exactly one path, right? And so this is, the case of a tree. Is that a tree? Is that a tree?
Yes.
It is, right? Because it doesn't have any cycles, right? And you choose two vertices, right? And there's always one path, right? Between any pair of vertices, right? So that's another definition, an important definition, right? That is a tree, right? And what is a weighted graph? What is it? Well, now you have a triple, a graph is a triple, vertices, edges, and weights, right? Where V and E is a graph directed or undirected, and W is a function from E into R, right? For each edge, there's a value, right? Representing something, right? For an edge E, WE is called the weight, right? The weight represents, as I was mentioning before, the weight or distance or cost or a kind of measure, right, of something that is representing, something related to the specific problem that you are simulating in a graph, right? And this is a weighted graph, right? So we are going to do some algorithms in which we have weights, right? Weights. So questions so far? Are we doing okay? Everything clear? Easy concepts,
Yes.
right? Easy concepts. And I'm sure that you've seen this before, but we need to formalize, and then we're going to move on to some algorithms, right? For solving specific problems. So if I want to represent a graph in the computer, right? I have this graph, as a model, and I can use an adjacency matrix, right? In which I have all the nodes, the rows, and all the nodes in the columns. And then I can say, well, if there is a 0 in the cell, means that I don't have a connection between this node and this node. For example, I don't have, for example, D here is the only connection between D and D, right? There's a 1 there. There's a connection between A and B, and this and this one, right? For example. So this matrix is going to represent the graph somehow here with 0 if there's no connection between the two nodes, or 1 if there is one, right? And sometimes I can use the adjacency matrix, and if I'm representing the weighted matrix in the cell, I'm going to just include the value, right? Representing something, right? Here, what is the advantage of representing a graph in a matrix like this? What do you see as an advantage? for that representation. What do you think is easy to do here in this representation?
Can you repeat it? You broke off on the last one.
The question. You know, what is the advantage of using this representation, the adjacency matrix as a representation? And I'm talking about a computational aspect, right? What is the advantage? If you're going to do something and you're going to program, you know, this graph or an algorithm for this graph in a programming language, and you have the representation of an adjacency matrix, what do you think is easy to do with this representation?
Well, because you can multiply, it's a matrix, you can multiply it, add two matrices, and also this represents a distance matrix, which you can automatically pass to other methods.
You can go easily and say, well, for example, if I want to say something about D and F, right, I just go directly to the cell, and the cell is going to tell me something, right? It's going to tell me if they are connected or they are not connected, right? So it is easy just to access the cell and say, okay, I have information about that, you know, that connection between the two nodes, right? And it is easy to say here because you go straight, you know, to the cell, right? And the disadvantage for doing this representation, what is it? If you talk in terms of space, what are you using here?
Memory, too much memory.
You're using memory, right? And sometimes you say, well, if I have a lot of connections or a lot of zeros in the representation, right? Probably I'm just using or I'm just wasting a space, right? Because I don't need all the space because a lot of connections are zero, right? And you're still using the space. But well, it depends what you're using and it depends what you want to use, you know, for solving the specific problem. But this is just an issue that you have to consider there. Because the other representation is using an adjacency list, right? And you just have the elements here, and then you have a list for each one telling you, you know, the elements that are connected to this node in particular. So, do you understand this representation? Do you think that this representation is the same as this graph somehow? What do? You have the adjacency matrix and then you want to delete one connection. What do you do in the adjacency matrix?
You search for the connection you want to raise and you change it from one to.
Well, you just go there, right, to that cell, for example, and then just put a zero, and that's it.
Yes.
Right? And here, right, it's not that easy, right? If you want to delete the connection between B and C or this E and F, well, not that one in particular, maybe. But for example, yeah, C and B, right? C and B, and you delete this one. What do you need to do? Start here and then go there. Is that B? No. Is that B? Yes. So you have to delete this and update the pointers there. So it's not that easy, right? What is the advantage of this representation now?
Less space.
Less space, right? but is a little bit more.
And also, if you say, save it, for example, in a hash table, search is faster.
So you use the hash table is that you're looking for an element and then you have a connection to that, and then there's something like this, right? You know, for those elements that are the same way connected. Right. So there's also, you know, advantages and disadvantages, right? So, but it depends what you're solving, right? And what is more suitable, you know, for the application that you have. But you can use these representations, of sometimes you can use an even more complex representation, data structures, right? To put your information there, right? But usually when we are using a graph is these two elements, but it depends. Now we're going to move to search algorithm in graphs, right? And this was one question by Cesar just a moment ago, right? And this is the way, is a strategy for looking, you know, something in a graph, right? And sometimes I can approach the search by using breadth, right? And breadth first search works in this way. You find all the nodes at the current level before going any deeper. So you explore, you know, you search by level, right? Level. So if you don't finish exploring all elements here, you cannot move to the next level, right? And that's the way it works. So for example, you start in this node, and then you're going to search by level. You finish that level, and then you continue in the next level, right? By level, yeah. So if you are using a data structure to represent the search, what kind of data structure you're using here? What do? You put this one in the list, right? You explore it, and then you have these two, right? And then you explore this one, and then probably you're going to include this. And then I continue with this one, and then the other. So what is the kind of queue or list that I'm using here, you know, to represent the search by level, the search by breadth first? What is the kind of list that I'm using here? What is that? In the search, in the breadth first search. What is it? Have you heard?
Like a heap?
Of this term? What is a queue in the movies, theater? When you go and buy tickets to the box office, what do?
You
What
wait.
is a queue? First in line, right?
Yeah.
First serve, right? Second in line, second serve. Third in line, third serve. So this is the way. This is a queue, right? In terms of computer sciences, first in, first out, right? Does that make sense to you? So we are using a queue to represent the breadth first here, right? Because I'm aligning the elements in a queue, and then I'm attending but I'm going through the elements according to this way, right? I explore this one first, and then these two, and then these four in this direction. So this is a queue, and is, you know, the strategy is first in, first out, right? Is that clear? Yes?
Yes.
Okay. And the other strategy is depth first search, right? How does it work? Well, you follow a branch and go as deep as possible before trying any other branch, right? So you go deep. If no about options, backtracks and continue to other branch, right? If the search gets to a dead end, it returns to a previous state, right? Like this. And this is called, in computer science, is called backtrack, right? So you reach the end, and then you backtrack and continue looking for different branches in the tree, right? Yeah, at the end, what you are constructing here with the depth and the first and the depth and the breadth first search is a tree, a search tree, right? So in this case, you go here, and then you go here, and then you go deep, no more. So you backtrack and then continue in that branch, right? No more, backtrack, and continue on the other branch, right? And then continue deeper, no more, backtrack and continue, right? And then you say, no more, backtrack, no more, you stop there, the search, right? So you are traversing in this way, and then in this way, and then in this way, and then this way, backtrack in here, right? So you go as deep as possible, right? Before trying any other branch. That's the idea with DFS, right? So if I say I have a data structure helping me, you know, to emulate the search, what is the kind of structure that I'm using here? Have you heard of the structure stack? What is stack? How does it work? A stack of books? What is that?
One on top of each other.
Yeah. So what you are putting here, several, and then you start, you know, popping out from the stack. And what is the one that is you're going to choose in a stack?
The last one you put Laffy or something like that?
Yeah, LIFO.
This way. Last in, first out, right? So that's the reason here. You put this one here, right? And this one, and this one. No more, you check it out, right? And then you continue this one. You go and check it out. And then you go this one, get out, etc. Right? But you're using a different strategy as the one we used in the breadth first. So with this structure, we are going to have this behavior, right? Going deep, backtrack, right? Going deep, backtrack, etc., right? So we're going to have a LIFO queue, right? a list of data structure, like last in, first out, right? Now, try, this. You have this graph, it's undirected graph, and then you say, well, I'm going to start here, right? And I'm going to use a breadth first search. So what should I do? What you need to consider here, the way you are going to choose the nodes is lexicographic, that is in alphabetical order, right? For example, you're in A, and what is the element that you're going to put in the
B,
and then
C, and then D.
so you explore like this level, right? The ones that are connected to A with just an arc, right? And then you can go from there, you're going to choose which one.
J.
The ones that are connected to D, right? First, and then you have B to J, right? So you explore this, and then you go to C and you explore G, and D is already there, right? It's already visited. So you're going to have an A is already visited. So you go to G, right? You have this, right? And then you go to D, and D, you have this already visited, this already visited, and H here, right? And then you say, well, I go to J, and J, D is already there. And then G is here, so I go to E, right? And then I go to H, and H is F, right? And then E is to F already, and to what is this? G. So the last one is going to be I, right? B, C, D, J, G, H, A, E, I. Oh, I made a mistake or what? J first, no one there. And G, yeah, you have I here. And then F, yeah, this is the right way, right? But I'm using PFS, right? Question for that. Is that okay? So that's the way it works. Breadth first. And if I want to use DFS, I start here. What is next in the search? DFS. What is it?
B,
B,
then J,
J. I go as deep as possible, right? And then
C,
I need to continue from here, right? I still have this connection, right? Is that
okay, yeah,
clear?
yeah, right.
And then I try to use this one, but it's already visited. So I use to go C,
H,
C, right? First, lexicographical scheme, right? C, right? I go to C first before H. You see? Here. And then C, this one is already visited, but I can go in G, right? And then E, and I still can go F, and I can go F, H, or I. H first, right? And then no more here, backtracks here, F, I here. Does that make sense? So I go as deep as possible, right? First, if I reach a dead point, I backtrack, right? And then I continue, like in this case, right? H, and then no more, I can go and backtrack, but I still have a path here to I. So that's the reason I visited H first and then I there, right? So this is depth, right? This is the way it works, right? The DFS for this graph in particular. So questions? Sorry, I don't, there's a question here. Okay. So what do you think? It's easy, right? So a Q for BFS, stack for DFS, right? It's what I'm using inside the algorithm, right? For this kind of search. Everything okay?
Yes.
I will give you this exercise. You can do it later, right? That you can try. Right now, I have a what? A graph, right? So it's going to behave more or less the same, except that, right, I need to look for the direction of the graph, right? For example, for BFS, I'm starting here. I have two options, S and T, right? Where I should go first in BFS. So if this is Q, right? I go where? I have two options only from Q, right? This direction S and in this direction T. So I kind of S, right? And then T, I don't have any, okay, I have W here also, right? Something like this. And then I choose S first, and then T, then and W, and I'm just starting to put things here. So you can just check it out, right? And you're going to get something like this, right? And this is BFS for a diagram, and this is BFS for diagram. So, you know, the traversal is a little bit different, right? Okay.
Is this going to be just an exercise, or this will be the homework number 8?
No. It's just an exercise, just
Okay,
for you to test. No,
okay.
Exercises are coming up later, right? The homework. All right. This is just for you, you know, just to make sure that you understand doing BFS, DFS in either a graph or a diagram. So these are just examples, you know, for those concepts. Is that okay?
Yes.
Okay, good. So let us just move on right now. When I'm doing search in a graph, I can classify the edges that I find, you know, as I go, through a specific search. For example, I'm in a node here, and then I'm moving, and I find this node for the first time. So a 3H represented by, this solid arrow containing vertices P and vertices vertices U and vertices P, that it was first discovered by the exploring edge UW. So this is U and this is P. So if you are traversing, right, you are searching, and you find for the first time this connection, this is going to be a tree search, right? Because it's like I'm forming the tree with these edges that I found for the first time, right? So this is called the tree edge, right? And then the other kind of edge that I can find in the search is a back edge with dotted arrow. And are those edges B and W, B and B, I'm sorry, U and B, sorry, U and B, right? Connecting a vertex U to an ancestor B, something that I had visited before, but this one is going to find this edge from U to B, U to B, in such a way that I'm going to connect this, but to an already visited ancestor, which is B. So this is going to be a back edge, right? So this is the first time. This is when I connecting to an ancestor of U. Or in other words, this B has already been visited before, right? We consider self-loops, which make occurring directed graph to be packages, right? For example, I have this one, and this is going to be a package, to the same node. Now, the other kind of edges that I may find in the search is the forward edges, right? Are those non-tree edges, right? Non-tree edges, not like this one, not like this one, but they connect U and B, connecting a vertex U to a descendant of B, right? So it's like you have this U, and you are going to connect somehow with a forward edge to this descendant of B that is already visited, but is a descendant, right? A descendant means that it's forward in the tree. It's not backward in the tree like this one is. This is forward in the tree, but it was discovered before, but this one later connects to this node U to this node B, right? So these are forward edges, right? And the other kind of edges that we can find is, with this waving arrow, are all other edges. They can go between vertices in the same depth, first tree, right? As long as one vertex is not an ancestor of the other, or they can go between vertices in different trees. Sometimes that happens. I have a node here, and this belongs to a tree, and this is another tree that I explored already, and there's a connection between this and this. So this is a kind of cross edges, what it's called here, right? So those are the different edges that you can find, when searching in trees, right? And now, observe this. Observe this, right? Let us suppose that you have one here, which is the 3H, back edge, forward edge, cross edge, right? And where can I find this kind of edges? Let us observe this. If I have a graph here, and I have a diagram here, and I have BFS here, and I have BFS here. So, for example, if I have an I-graph, right, and I'm doing DFS, depth first search, I can find all kinds of edges. See? If I have a graph, an undirected graph, and I'm just doing DFS, I'm going to have just 3 edges and back edges, right? For BFS and graphs, I'm going to have 3 edges and cross edges, right? And if I have a BFS here, and I have a diagram, right? I have all edges except, what is the one, number 3? Forward edges, right? I don't have that here. Now, this is an exercise in the homework. Try to explain why these edges in each cell. Is that clear, the question? Right? You see, it depending on the graph or diagram or this kind of search that you use in DFS or BFS, you're going to find a search tree somehow, right? And then this tree is going to have this kind of edges, right? So you try, for example, try DFS first in a diagram, and then you will find all the possible edges. I don't know if I have an example here. No, I don't think I can. But you try an example with this and try to explain the exercise that is in the assignment. Okay? Questions so far? Everything okay?
Sorry, Professor. What is 1 and 2 referring to?
1 and 2 is 3 edges, back edges, forward edges, cross edges.
Thank you.
All right? All right? So there's a definition for each, but if you do an exercise, I would recommend to use a diagram and try to to traverse with DFS and try to find all these possible edges, because it's a case in which you have all the cases, all the kinds of edges, right? Right? But also try to understand and explain why, for example, for DFS, if I have a graph, I can only find a 3 and back edges, right? So is the question clear? Or not?
Yes.
All right. Okay. So that is good. Okay. So that's all with respect to search. Now let's do some problems and algorithms, right? Let us do this one first. What is a spanning tree? What is a tree? We said that it's a structure, or what is the feature, the main feature of a tree?
It doesn't have the cycles, right? You're
Doesn't
just
have
connected by
cycles.
one path.
That is correct. Yes. Okay. And spanning is, expands in all the nodes in the graph G. And the minimum is because we have a weighted graph and we are looking for a tree that is the minimum or has the minimum weight. The spanning tree for a graph G is a subgraph of G such that is a tree and contains all the nodes in G, right? So that's the first definition, a spanning tree. And the minimum spanning tree is the tree with the smallest weight among the spanning trees of graph G. Okay? What we are going to find is the minimum spanning tree of a graph using a particular algorithm, right? So, is it clear what a minimum spanning tree is? Is that understood? First, you have an original graph, and then you're going to say, if it is going to be a spanning tree, should contain all the elements in a tree, right? And if it is going to be the minimum, it's going to connect all the nodes, right? And the weights that you are going to have here, the summation of all the weights in this tree is going to be the minimum, right? If you want to apply this structure of a minimum spanning tree, where would you apply? What is it good for? To get the spanning tree, you have a connection of what? You have a connection of what? What are the nodes representing? Can be a network of computers, right? Can be a what? A network of airports, for example, right?
Professor, can you explain again the concept of a spanning tree?
Yes.
I get lost.
Okay, let
For
me
example,
just go back.
A graph G, and
You have a graph G with vertices and edges. And actually, if I'm going to get this one, I'm going to have weights also, right? But first, I go back and so is it clear what a tree is inside a graph G?
Yeah, undirected
and the
graph.
condition is that I don't have a cycle, right, in that structure. That is a tree, right?
Yeah, right.
And then the second is that the tree is going to contain all the nodes in G. Is that clear?
But if you are taking a subgraph of G,
No.
the
I'm not
tree
taking.
must.
So that's the condition is that I'm going to, yeah, of course, I'm going to take a subgraph of G, but that subgraph is going to contain all the nodes in G, not all the edges necessarily, right? But all the nodes,
Okay, yeah,
right?
that's right. Yeah,
I'm
right.
gonna take off possibly some edges, right? But at the end, in order to be spanning, is that it's going to contain all the nodes in G, right?
Yeah,
That's
you're
the
right.
second condition, right? For determining spanning here. And what is the third condition to getting the minimum? Well, it's the spanning tree minimum, right? It's a tree with the smallest weight, right? Among all the spanning trees of G, right? Means that I have weights in the edges, right? And I'm trying to find a tree that connects all the nodes, but has a minimum weight. Is that okay? Is the concept okay?
Yeah. Is this related to the traveler salesman problem?
No, not really.
No?
No, it's
Not
a
really?
different problem, but it's still, we use a graph, right?
Yeah, right.
And you're going to realize the differences of these problems. Maybe later or in another session we're going to have eventually, right? So there's this algorithm. Now it is an algorithm by finding the minimum spanning tree, right? And you will see, you will understand. Orders the edges by weight from smallest to largest. So you choose all the edges, right? Order all the edges, from smallest to large, minimum to maximum weight, right? And then you go this way, inserts the edges one by one in the MST, avoiding cycles until all the nodes of the graph are included in the MST. So you are constructing the MST one by one. So do you understand this step? Do you understand this step? That's the cross-counts algorithm, right? Do you understand this algorithm? We can proceed further, in which we have an example. Do you want to go to the example and try to understand the whole concept already?
Yes.
Okay, let us go. So I have this graph, right? So do you agree that this is a G, is a B, is E, and actually it's a W also, right?
Yes.
So I need to find the minimum spanning tree. So it is a tree. It won't have cycles. It's going to be spanning because it's going to contain all the nodes in G, right? And also it's going to be the minimum. It means that, once that you sum up all the edges in the MST, that value is going to be the minimum that you can get, right? So what we are going to do is order all the edges, right, from smallest to largest, right? Clear enough? Is the first step in the algorithm, right? Order all the edges, right, from smallest to largest. What is the second step in the algorithm? What is the second step in the algorithm? Remember? We need to go by one by one and gradually construct the tree, right? So we're going to choose this one first. Can I put it in the tree? ED. What is that? ED. This one. Is that okay? Does it violate anything related to, for example, having a cycle?
No.
No. Right. So just put it there. Right? I continue. IG. IG. This one. Any cycles?
Nope.
Right. AB. Any cycles? No. CD. No
You're
cycles.
fine.
CH. Oh, CH. No problem. Right. EI. EI. Any cycles? No. AG. No cycles. Right. GH. You see, GH, right, is constructing this cycle, right? So that's the reason I cannot include it in the MST, right? So you see the reason there why we are not including GH, right? Because it constructs a cycle there. And we see the same, right? See this one. So there's a cycle there, right? Here, 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 and here. So I don't include that one also. HI, now this one is constructing this cycle, right? If I, that is okay. Where is it? This, and white 5. And still, I need to connect, okay, so up to that point, actually, you know, you had all the nodes included in the MST, right? So you have this, and is that a tree?
Yes.
It is. Is that the minimum spanning tree?
I don't know.
Well, it's what the Kroskal algorithm is doing, right?
Yeah.
So it guarantees that you're going to find the minimum spanning tree. And the reason is that you are going in this way, you know, from smallest to largest, trying to, you know, one by one insert the edge that, you know, it's a kind of greedy algorithm, right? Because it's choosing the minimum every time. And it's at the end, you're going to have the minimum spanning tree, right?
Yeah, right. What's the complexity of this algorithm?
Okay, you tell me. That's my question for you. What do you think it is? What is the cost of ordering, you know, all the edges?
N log n,
What is n?
the number of pairs in the graph, the edges.
Number of edges, right? So it's the cardinality of E, right? What else?
Yeah, right.
Log base 2 of what? This?
Yeah, and also multiplied by, I don't know, maybe something, because you're doing the sorting process iteratively.
This is the sorting, right? All the edges, and this is the number of edges that you are going to sort, and this is, you know, the complexity, E log base 2 of E. And then you do pretty much the same again. You traverse all the edges, possibly, right? And if you want to put this complexity in terms of n, what would you do? What is the complexity of E for a complete graph, for example? This is a good question for the exam, right? What is this? You know, a complete graph with E edges and n nodes, right? Which is the case. What
And
is
minus
it?
1?
N minus 1 over 2, right? That's the worst case when the graph is complete, right? So this is kind of n squared log base 2 of n squared plus n squared, right? Does this expression make sense to you? So what is the complexity? These two, you can just move it, right? So you're gonna have 2n squared log of n plus n squared. What is the complexity of this? N squared log of n, right? That is a little bit higher than n log n, right?
I
You're
have a
sorting.
question.
Yes.
Why in the complexity, after you sort, we don't include at each level checking if it makes a cycle? Wouldn't that also be
Well, yeah. But you do it when you somehow have a structure that you are using some operations there. If you want, you can just consider it, right? But
Okay.
it's not going to affect this.
okay?
You may say that I use a number of operations, but it's going to be, I don't think it's going to be that much. Okay.
Okay.
You can say that it's a constant. But it's a good question, right? Sometimes because in the algorithm, sometimes I use some operations, additional operations, but at the end, what you have to consider is if that number of operations really affect your complexity, right?
Yes.
So is this okay? Or this okay? In order, now you have to, you say, well, you're sorting, it is true, but what is the amount of elements that you are sorting? Well, E. Okay, but in terms of n, this is like this amount, which is n squared. If I want to put everything in terms of n, because n is at the end the size of the graph, right? And the algorithms, remember, are measured according to complexity in terms of the size of the problem. And in this case, the size of the graph is, representing the size of the problem. So we say a graph with nodes, that is the most important measure, to say what is the size of, the problem that you're tackling, and that is related to, a specific constraint, a specific complexity of the algorithm, right? So this is an algorithm for doing, the spanning tree, right? Can we check a second one? Can we?
Yeah.
Okay.
Yes.
So the diagram thing algorithm, also for this minimum spanning tree, works in the following way. You have different vertex types. Tree is the tree built so far. We are going to construct the tree gradually again. And so you have the tree, and the tree is going to contain some nodes and some edges, right? The frontier candidates, not in the tree, but adjacent to a node in the tree. So these are frontier nodes, right? They are candidates. And unvisited, the rest of the nodes in the tree. So the algorithm is going to work as follows. Initialize all the vertices are unvisited. All the vertices are unvisited. Choose an arbitrary vertex S, right? Place S in the MST. So the MST is going to start with just one node and an arbitrary node that you chose from the unvisited ones, right? And then reclassify the adjacent vertices to as a frontier. So choose the nodes connected to this S, and they are the frontier vertices, right? And there's some several that are, this is frontier, and these are frontier, and these are unbasic, right? And then the main loop, as long as there are vertices of type frontier, select the edge of minimal weight between a vertex 3, T, and a frontier vertex W, right? So you can imagine that you have the vertex, the MST here, and it's connected to some frontier, right? And you're going to choose the minimum weight or an edge with minimum weight, connecting elements in the MST and elements in the frontier, right? Reclassify V as a tree and add TV to the MST. So you're going to choose the minimum weight, choose that element in particular, and put it in the MST along with this edge, right? So reclassify V as a tree and TV, right? The element in T connected to V in the MST, and reclassify all the unvisited vertices adjacent to V as the frontier. Now I have again the frontier, the MST, and then the frontier, and then I continue, right? As long as there are vertices of type frontier. Otherwise means that I have all the elements here in the MST. So what do you think of this algorithm? Hmm? Do you think that is different from the previous one, right? From the cross-bell algorithm. Works a little bit different, right? But it's still easy, right? Do you understand the algorithm? Yes or not?
Yes. Is it optimal, Professor?
That's a good question. Let's check it out. First, you have to tell me the complexity of this algorithm. What is the complexity of this algorithm? Hmm? You don't sort here, right? What is the main complexity coming from? Hmm? Here. What do? Tell me the complexity of this algorithm.
Well, you first will check for all the edges according to one root. So it will be n minus 1 edges.
But
And
not
then,
all the edges are connected, right? You are trying to find. So you put all the nodes unvisited first, and then you choose one, right? And then just check what are the edges connected to this node, right? If you
yes.
say, if the graph is complete, you may say, well, it is connected to all the other nodes, right? How many?
N minus 1.
N minus 1, right? And I choose just one, right? Which one? The one with a minimum weight, right? And I have, in the second step, I have this MST, right? And I say, the frontiers I have n minus 2, right? Connections, right?
Yes.
Because I have n minus 2 elements here, right? So what is the complexity of this algorithm? Do you understand this? But what you can do is, do a process, just to get the minimum very quickly with n minus 2 or n minus 3 steps, right? Or comparisons. So what are you getting here in this algorithm? At each step, n minus 1 comparisons to get the minimum, right? N minus 2 comparisons to get the minimum. N minus 3 comparisons to get the minimum. So it's going to be like this. What is the cost for that? What is the cost for that? What is the summation of I? N minus 1, n minus 2, n minus 3. So
N.
it's from 1 to what?
To n.
To n minus 1, right? So it's going to be n to n minus 1. Going to be something like this, right? What is the complexity of that? What is the complexity of that summation?
Approximately.
Square.
Okay.
N squared, okay. Now, you have to consider here that, in this case is clearly Sn minus 1, right? Because there, if you're connected this node to this one, is, there's only one connection here for each node that you have in the frontier. And then when you have two elements here connected, so you have, you may have this and this, but with a constant, you can just eliminate you can just get the minimum here, the minimum here, the minimum here. So it's going to be 2, right? Or just one comparison in order to eliminate. And then it's like in this one, you're going to have 3, and this is connected to n minus 3. So it's like the number of elements is reducing, the number of comparisons maybe is increasing, but you can handle in your algorithm to make it more efficient in order to have just a constant number of comparisons there. So that's the reason that this algorithm is going to be n squared. And this is better than the previous one, right? In the other one, what we had n log squared, n squared log of n. In this one, I have n squared. The question is if this algorithm is optimal. I don't know. I don't remember the demonstration for doing that, but it's a good question indeed. So I would think that tends to be optimal, but I don't know if there's a better algorithm for doing this process in a better way. You know, this is the best algorithm that is reported in the book. So I would suppose that, but I don't guarantee that it's optimal. You know, I'm sorry, but it is true. I have to be honest here. All right. So what do you think? Same problem, two algorithms, different algorithms, right? Okay, let us take a break, I think. And let us return at 5:55. Is that okay?
Yep, that's okay.
Okay, good. Okay, let me just stop recording here. Okay, we're gonna continue. Okay, so this is an example of the Dijkstra-Krems algorithm, right, for finding the spanning tree, the minimum spanning tree. So it's going to start here, right? And then, you know, the frontier nodes are C and D. So from this, it's going to choose the minimum, right? So it's going to, you know, include C in the MST. And these two are connected to this only frontier. So it's going to choose 3, right? And now up to this point, we have this as the MST, but we only have one connection to this frontier. So it's going to be included in the MST here, right? And then D is connected to 3 other elements. So those are the frontier, right? And then you find, you know, the minimum of this, which is 2, right? And then you have, from this, you only have 2. And then you choose this one, right, on the, well, you have, yeah, this is a frontier also, right? And then you include at the end, you include F, right? So this is the minimum spanning tree, right? Obtained with the Dijkstra prime algorithm. So for this algorithm, you know, for the graph algorithms, what I need you to study is, you know, the problem and then the algorithms that we have, right, basically. And the idea is that you can apply those algorithms, you know, in different exercises that you're going to tackle. All right. So this is just an example, you know, for you to do an exercise with this algorithm. In fact, you can apply for this graph, you can apply both Kruskal, and you can also apply the Dijkstra ring here, just as an exercise, okay? Now we're going to move on to a second problem, which is the shortest path algorithm. The shortest path is you have the origin here, and you have the destination there. And then you want to find a path, right, that is connected the origin and the destination, but with the idea that is going to be the minimum, you know, the shortest path, because we have a graph that is weighted also. And the idea is to apply this algorithm. So let us suppose we have a graph with a set of vertices V, and we are going to enumerate all the nodes from 1 to n, right? So we have n vertices actually here. So we're going to enumerate all the nodes, right? And then we're going to have two classes, right? The first one is the vertices for which the minimum distance from the vertex 1 has been calculated. So we are going to have a set of vertices, right? For which the distance between the number 1 to this one is the minimum, is the minimum, is the minimum. So this is the class 1. In the class 2, those two vertices left to examine, they have a value that represent the shortest distance known at that moment in particular, but not necessarily the minimum value yet, right? So we are going to work as follows. Assign vertex 1 to class 1 and the rest of the nodes to class 2. So again, so this is class 1 and this is class 2. And in here I have vertex 1 here and all the others in the class 2, right? Now assign 0 to vertex 1. So the minimum distance from the vertex 1 to the vertex 1 is 0. So that's the reason. And assign an infinite to the rest of the nodes, right? So that's the value that they are going to have at the beginning. Repeat until n is added to class 1. N is the destination node, right? When we are going to put it in class 1, we are just to ensure that the value is the minimum for that node, right? Define the pivot vertex as the most recent vertex added to class 1. So this is the pivot, the most recent that I added to class 1, that is going to be the pivot. And then adjust the vertices in class 2 as follows. So we are going to do some adjustment. If the vertex is not connected to the pivot, right, its value doesn't change. All right? If it is not connected to the pivot, it's going to remain the same. If the vertex is connected to the pivot, replace its value with the minimum of current value or the actual value of the pivot vertex plus the distance of the pivot vertex to such a node, right? So it's the pivot is going to have a value and is connected to this node. So we are going to add the value here plus the distance between the pivot and this node in particular. And that is going to be, you know, the value that we are going to compare against the current value. And then we are going to just assign that minimum value to the node. Select the vertex in class 2 with the minimum value and move it to class 1, right? And then we are going to repeat. We are going to repeat, right? So do you understand this algorithm? We are going to run a small example for this to understand better. Is that okay? Yes?
Yes. Yes.
So find the shortest path between B and G, right? B is here and G is here, right? So this is going to be in class 1 and all the others, and this is going to be 0. And all the others are in class 2 and they all have infinite value, right? Let us move on here in the steps. So B is the pivot, right? All the others are an infinite. And then we are going to check the nodes that are connected, right, to B. I'm going to return the ones that are connected to B is this one and this one, right? And the value here is 0 plus 7, and here is a 0 plus 2, right? Compare against infinite is going to be 2. Compare against infinite is going to be 7. So that's the reason I have 2 and 7. All the others remain the same, right? Clear so far? So the one that we are going to choose as a pivot is which one? Which node? This is already in class 1,
B.
right? And I have 2 connected to that pivot. And then the one that is going to be included in class 1 is going to be C, right? And remains the same, and this in infinite, right? So the nodes that are connected to C, let's see here. The one that is connected to C is A, right? And what? A and E here, right? So this is going to be 2 plus 4, now it's 6 instead of 7. And this is infinite, and this is 2 plus 5 is 7, right? So those are the values that I have here, 6 and 7, right? And they are connected to C. So what is the next node to be chosen? What
A.
is the next? A, right? Because it's the minimum between these two, right? So it's 6 is already, I have 6 and I have 7. So this is the one that now, you know, the ones that are connected is A, right? And A is connected to, I'm sorry, A is connected to G, right? And A is 6 plus 10 is 16. And then D, which is 6 plus 4 is 10. And that's it, right? These two. Okay? You see? 16, 7, and this remains the same, right? And the minimum is going to be the 7,
E. Mhm.
E, right? And this remains the same. So 7 and 7 and E is connected to F right here, connected to D already there. But the 2 plus 5 is 7 plus 3 is 10, and the 6, 4, 10. So it's the same. So you can keep it there, 10. And the 14 here, F is okay, so you have here 7 plus 7 is 14, this one. So that value is going to change, right? And it's already there, and it's already there. So the minimum of this is going to be this one, right? And then we continue, right? The smallest one is going to be this one, and this is there, right? Is the final, because we got the minimum from here to here. So this is in class 1 already. So that's the minimum value for the path between B, and G. Now, what the algorithm is doing is like, going for different paths, right, until it reaches the destination goal. But what is it finding is finding the minimum from, the root or the origin to that value in particular, if these nodes are in class 1, right? For example, this one is going to stay there. If you want to continue to find the minimum and put it in class 1, you can do that. But up to this point, you're not sure if that value is the minimum, right? For that node in particular. But this is the way the algorithm works. Can you more or less imagine the complexity of this algorithm? What is it happening? What are you using, to construct the solution for this algorithm? What are you using? Number of edges, right? Is that true? I don't sort or anything. I'm just constructing, right? And trying to find, the pivot and the ones connected. Pivot, the ones connected, but this, the connections, the nodes in the class 1 is increasing, while the number of edges connected to the members of the class 1 are somehow decreasing, right? So I would say that this algorithm is going to have something like n squared or more is the cardinality of V, or less what you are using here. Okay? This is what you find here. Now, okay, this is another algorithm, another concept, right? So we talked that we have connected components in a graph, right? Means that I have possibly different subgraphs in which the elements here are connected, the elements here are connected, the elements here are connected, right? But not necessarily between this and this and this, right? And the idea with bi-connected is that we have at least two connections between any pair of nodes in the subgraph, right? For example, you have a network of airports, and if one airport closes, you still have the possibility to fly between any pair of cities, right? In that component, right? So that's the reason is that component is bi-connected. So I still close one, but still, can find a path between any pair of the other elements in the byte component, right? If a server is down, it is possible to send messages between any other part of sites. That's the idea with this problem. And with the algorithm for finding by connected components. For example, right? So the problem is in general, it's given an undirected graph, GVE, if any vertex and the edges connected to such vertex are removed, is the remaining graph still connected graph? That's the point. That is the intention of the bi-connected components, right? And you need to find, the bi-connected components. So that is a bi-connected component, and the articulation point is something in which if you are going to connect a bi-component with this other, all the paths between an element here and an element here is going to be passing through this articulation point. So that is the definition of the articulation point, right? And how this algorithm work? Well, this is what we are going to explore in the next slides. All right. So it's let me just show you the example. For example, you have the whole graph here, right? And you are trying to find the by connected components of a graph, like this. So what you're going to get at the end is, this, because if you eliminate this, you still can fly from this to that, right? If you eliminate this, you can fly from this to there, right? If you eliminate this, you can fly, from this to here, to here, to here, etc., right? Those are bi-connected components of 3 elements or more. And this is a special case in which you have a bi-connected component, but is called a bridge. Means that only has 2 nodes in the component. So, but it still is considered a bi-connected component, right? And this, for example, this one is articulation point, this one is articulation point, this one is articulation point, because if you want to go from this bi-connected component to this element in the other bi-connected component, you have to go through this one, right? So that's the idea. It's the same here, right? If you want to go from one of the elements here to one of the elements here, you have to go to this one in particular. So what you're going to get in the algorithm is, given this graph, you're going to get these 4 bi-connected components, right? So let us check what the algorithm is doing, right? So there are 2 phases in the algorithm, right? The first phase is to traverse the graph, right? Using depth first algorithm, right? And what you're going to do, right, is just complete the depth first search 3. And what you're going to do is to add 2 numbers to the to each of the nodes, right? One is the order in the search, right? And the other is this is the DFS order, and this is the back value for that node. And what the algorithm is going to do is, trying to find with 3 edges and back edges, like, I can reach this point to several nodes with 3 edges and back edges. And then at the end, it would say, well, this component has all the features that I need for a bi-component, means that I can connect this one to this one, and even if I just break one of the edges, right? And then it's going to try this, like the clusters of nodes in a bi-component, right? That are somehow separate through an articulation point with the other components. So this is what it's going to do. So in the first phase, it's going to do the depth first search tree first, and it's going to be the order here in the search, right? For example, let's do the depth first search of this tree. So it's going to start here in A, right? That is going to be the order 1, and then it's going to find at 3H, and then it's going to be D, the second node, the second value, and then F is going to be the third value for F, and then it's going to find a package here. Nothing is going to change, right? It's going to continue, and it's going to continue here. So this is 4, 5, 6, right? And this is a back edge. It's going to backtrack, and then 7 here, right? 8 here, package here, backtrack, 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 right? And then 9 here, right? And then backtrack 10, right? A back edge here. Okay, it found an edge also back edge over here. So the order, the tree is going to have a 10 a number nodes, right? And the other thing we are going to do in the first phase is to say, to include, I'm sorry, an additional number, an additional label for each number. So the additional label is going to be this. One is the order of the search, and the other one is going to be called the back. And the back is a number also here. So this is the DFS, and this is the back. And the back means how far I can go back from that node, you know, to an ancestor using 3 edges and back edges. For example, at the beginning, we are going to put, you know, the same number, because from this node, I can just go back to that same number, to the same node at the beginning. So this is going to be 2, this is going to be 3, this is going to be 10. You know, the back of those numbers is going to be the same, 4, 9, 5, 6, 7, 8. So at the beginning, I do the DFS, and then I assign the back to the same number that I found in the search. So that is the first phase of the algorithm, right? So is that understood? The first phase of the algorithm is going to run DFS, and is going to assign a value for each node, and that value is going to be the same for the other label that we are going to establish for each node, which is back, right? So that's the first step in the algorithm, right? Now, as we run, we are going to start again in the initial node, right? We're going to start in the initial node, right? And we are going to find, you know, we are going to traverse the tree, the DFS tree. So we're going to proceed forward, and then, you know, we have the values of the back, right? And then here we detect a back edge FA, right? And then let us see the conditions. Let us see the conditions. There are several conditions. So this is back of B is the same as DFS of B. So it's when we set the value of back the same as DFS for each of the values. That's the first step. When B is explored and one back edge BW is found, update B. B is found is here, and you find a back edge, right? from B to W, right? So what you're going to do is update in B, in this one, back B, back of this one, is going to be the minimum of the value that it has already with respect to the DFS W. So DFS is the label for the search in the DFS. So if this is an ancestor, means that you can go back from B to W, right, up to this point. So the value that you are going to, if this is minimum, is going to replace back of B, and it means that you can go back from B to an ancestor of that element, right? Instead of going to the same element, it's going back also to this element, which is an ancestor. And that is the way that you are going to start this, components. That's one of the conditions, for stating, the back B. So that is the thing you do here. When you start traversing here and you say, here I find a back edge from F to B to A here. And so I update back of F between the number that it has and the value of DFS, which is 1. So the minimum of those is going to be 1. So this is a new value for back of F. Back of F is going to be 1. It means that from here, I not only can go back to my to the node itself, but I can go to a node that is the ancestor of this one. So means that with this, I kind of constructing like a cluster, right, with those nodes in particular, right? So and then it's going, so these values are updated, but the search continues, and then it's going to go, continue forward, detect C and E, right? And okay, it's going here. See, it detects this back of H, C and E, and update back of C. So instead of the it's going to compare back of C is going to be 6, the minimum of 6 or the minimum of 4, which is this value, the DFS of E, right? So the value of back of C is going to be 4, means that it's connected to an ancestor and is trying to say something about this cluster of elements, right? Right, and then finishes here, and when it goes back, right, because it backtracks. So there's another condition here in the rules. Let's see. When returning from the search from W to B, the return value is called back W, right? So I'm returning from W to B, right? Now it's like this is W, and I'm returning in the search to B. I'm doing backtracking, but this already have a back W, right? And this has a back B. So this value back B can be updated, right, with the minimum of the value that it has already, with the minimum of the value of back, where it's coming from, because maybe this with a back edges, maybe the value is minimum than this. It's smaller than this because it can return to an ancestor that is up in the search. So that is the reason that back B is updated with the minimum of the value that has already with the minimum of the back of W, this element, right? And that is the case for this example here. So that's the other condition, right? let me see here. Here. When it's returning from W to B, so this is the minimum value of back, and this is the value of back W, and it's going to compare the both of those values, and it's going to say, okay, from this I can go here and I can go there, so I can go back to node number with label number 4, so I can just not only come back to the node itself, but I can go to this one and this back to this one, and I can come back to that one. And that's the way that this is like being constructed. So back of C is less than df. Okay, so now we are going to continue, right? Now we are going to follow the other condition we have. In order, to detect a biconnected component when returning from W to B again, check if back W, right? I'm returning from this W to B. If back W is greater or equal than DFS of B, if the condition is met, we can state that B is the articulation point and the biconnected component has been found. So let us observe what is happening here in this case. Here. So I return from here, I updated, for this, for B, right? And then I return from B to C, from back, let me see, back C less than the number of B. Let me just check now. Okay, I update here. No, we are okay now, right? And I'm returning. Yeah, I was returning and I updated, right? And I also checked the condition back of C, which is this, is less than df number of B, which is 5, which is less than the condition for finding a bicomponent, biconnected component is not yet, because this should be greater or equal than this one, which is not the case. So we are going to continue from there, right? In the other direction here. From B, we are going to G, right? So this is 5, 5, 4, and this is 7, 7, and this is 8, right? And you find a back edge here. So you're going to update this 8 with the minimum of 8 and the DFS of this V. So you update, the back of I, right? Which is this one, to 5. And then you go back from I to G, right? And still this 5 is less than 7. So nothing happens there. And then I go back from G to B, right? And I find that this 5 is equal than 5. So it means that I have found an articulation component here. And this articulation component is the head of this biconnected component here. So the component that you found is this one in particular, right? Because back of G, which is 5, is equal to dfs of V, which is that one. So this one is an articulation point, and this is a biconnected component. So this is the first biconnected component that you find, right? And then you continue, you go here, and then you go back from B, right? And then you find 4 is equal to 4, so E is also an articulation point, and you have another component. So, and you are going to go back, right? And you're going to find the rest, the remaining biconnected components there, right? In the same way. So you're going to find all these components in here. Remember, you studied in A. Well, this is not example, right? This is the example. So you had this one. So you have this one, you're going to have this one, and you're going to have the FME also. So what I want you to do is to do the same procedure until you find this one and the remaining biconnected components here. I think I have the solution of the whole thing. It's not here, but I will pass it to you through Canvas, you know, just to have the complete solution for this problem. That is the idea. That is the main idea with this algorithm, right? So questions at this point. I don't know if you follow me with all this. So if not, we can just repeat a little bit of these steps. Okay? Do you understand the first phase in which we find, you know, the first, the complete depth first search algorithm in the graph, which is this, right? I think we started here, right? With the depth first. Could you do that? Yes or no? DFS starting from here is what I told you here, is this, right? Is this. Okay? So you label the nodes according to the order in DFS. Right? So this is the first phase. What is the second phase? You start an A and you start, right, traversing. Right, traversing. And then you start checking the conditions. What are the different conditions? You're going to do first, you're going to do all the backs of the nodes equal to DFS of that node, right? That's the first thing you do. And then when you return you know, from B, when you find a node B and you explore back edge PW, right? You need to update the back B with the value that has with the value of the DFS of the W. So it means that you can go back from B up to this point or up to this node that is up in the search. When returning from the search from W to B, the return value is called back W. Then el back of B should be between the minimum of back of B with the minimum with the back of W. So you update the value. And then the condition for detecting the biconnected component is when you're returning from W to B, check if back of W is greater or equal than DFS of B, means that that value, right, that the value, the B is an articulation point and you have a biconnect. So that is the condition. So those are the elements that you need to check. So what I'm going to give you is a complete solution of this problem in order for you to understand, and then you're going to apply an exercise in the homework, you know, for doing this. Okay? Good. Questions so far? Questions so far? How are we doing? Yeah? Well, okay. So let me just give you very quickly two more algorithms, right? One is the transitive closure. And the transitive closure is, you know, you have a graph, right? And you have, let's say, connections between nodes, right? The transitive closure is, you know, this function in which you say, one, it is true if there is a path between I and J. I have I here and J here, and if there's a path between this and this, then I can say in my adjacency matrix that that cell is one. If not, right, then it's going to be zero. So that is a transitive closure, but it doesn't mean that, you know, you have a connection, direct connection, an edge between I and G. It means that you have a path. And what the algorithm does here is just to find paths between paths of size 1, size 2, size 3, and so on. And this is what the algorithm is doing here. So it's saying that if I find a path from here to here and from here to there, then there's a path from here to there. So that's the reason it is called the transitive, right? And this algorithm is doing that. And the algorithm has 3/4, so the algorithm is going to be like cube complexity. So this is what it's doing here, you know, finding partial paths from here to here, and then from here to here, and then put the things together and then saying, okay, if this is happening, so this is going to be one in my matrix in that particular cell. So that's the Warshall's algorithm, right? For doing that. And the other thing we find with is something like this. This is an example that you can go through it at home. And the other thing that we do with graph in general is, you know, we use graphs to model problems. For example, here I have the problem, which is an NP problem, and later we're going to discuss that, in which I have a graph, right? And the idea with this graph is to color the graph with a minimum number of colors in such a way that I don't color regions that are contiguous, means that they overlap. For example, this one, this one, right? So the idea is to, you know, color the regions in such a way, with different colors in such a way that you don't, you know, color regions with the same color that are connected in such a way. But you can imagine this one is easier, right? In which you can represent regions as nodes and connection between nodes as arcs. And then the color is, you know, the one that you're going to use just to say, I comply with the restriction that not two adjacent nodes are colored with the same color, right? Sorry, the redundant expression. So this one is easy, but imagine that you have this one. So you need to find, you know, the nodes and then the arcs, right, between the different regions and try to do this. And then you say, well, I need to color the graph in this way. But it is an NP problem because we can do this just heuristically, right? Usually. So we don't have an optimal solution for these kind of problems, especially when, you know, the number of regions or the number of nodes that you have is complex, right? And we can model, and, you know, you can imagine these problems of coloring countries with different colors if they are contiguous, for example, and trying to define the minimum number of colors you need to do that is difficult problem. I used back in my studies, in the PhD studies that I did, I had, you know, I needed to schedule exams, final exams, into slots. Say, this is Monday, this is Tuesday, this is Wednesday, Thursday, and Friday. And I needed to, you know, schedule exams, final exams in the slots. So I did a representation in what events are exams, right? I have a number of events, exams. I have colors, which are the different slots in which I can put the exams, you know, schedule the exams. And I have the constraints in which I say, well, B1 is connected to B2. It means that two exams and the idea here is that I have some students taking this exam and some students taking these exams. And I put a constraint because I don't want the students that take both courses, right, or exams in the same slot, the same color. So that's the idea. I cannot put, you know, exams connected with the same color. So I need to put them in different slots. So I model this for different benchmarks using an evolutionary algorithm for solving the problem. And it was just generating heuristics, you know, for solving the problem. The constraints are represented as arcs, right, in this case. So you need to solve the problem in this way. But this is a representation of a problem, you know, in a graph, and in particular, the graph coloring problem, right? So that was, I think, the solution, right? I have different colors for nodes connected, right? But when this number of events is large, you can imagine, you know, the complexity of the algorithm, right? So these are the conclusions, right? So we've seen topics and large applications, right? We explore different concepts, right? And we explore problems, MST, the bi-connected components, the shortest path, right? The transitive closure, and then in the emulation of problems into graphs also so different topics in this session, right? And now let me just go very quickly go to the homework. Sorry, took more time than I expected. Right. Homework. Yeah. Let me just say what you're going to do. Homework 8. So this is homework that can be solved in a couple. The first one is, right, in relation to the first one. It's, sorry, let me just, here we are. So this one is, you know, I have D, VFS, and DFS, and we have the categorization of edges, right? And then explain why DFS in a graph just 3 and back edges are found, DFS in a digraph all types of edges, BFS in a graph only 3 and cross edges, and BFS in a digraph all except forward edges, right? So this is the explanation of the table that I just mentioned in the slides, right? So this is the first exercise. Investigate the algorithm for computing the maximum flow of graph. So this is the problem. And try to find in the literature an algorithm for finding the maximum flow. And just put it there and try to show the algorithm with an example. That's the second exercise. And the third one, you're going to design a weighted graph with 9 nodes and apply the MST, right, the Kroskal and Dijkstra, and show the steps. So you're going to use just the 2 algorithms for finding MST. And design a graph, this is the fourth one, a graph with 4 components, 4 by connected, and apply the algorithm that we just revised. I'm going to upload the complete solution and show the steps, right? Design a directed graph and establish an origin and a destination and apply the algorithm of Dijkstra frame to find the shortest path, show the steps, right? And the sixth problem is the Euler circuit is an undirected graph in which is a circuit, right? A cycle that may go through some vertices more than once, and that includes every edge exactly once, every edge in the graph, right? So you're going to close all the graphs, all the edges in the graph exactly once, give an algorithm that solves this problem and the complexity, right? So this can be solved in couples, right? And you have to upload this. Remember, I think I stated the date as, you know, Monday just coming back from holidays, from Easter, but the actual submission date is, I think it's going to be, I think I put it there like the 20th of May, the 21st or so. So just check it out because homework 8, 9, and 10 are going to be due in May 20 something. I don't remember, but it's there in Canvas, right? So just previous to the exam, previous to the final exam. So that's the idea. Okay. So this is homework number 8. So don't worry about it at this time, right? Try to organize the solutions of the homeworks 5, 6, and 7, right? To complete that. And once that you submit homeworks on the 22nd of April, I will give you the solutions of all the homeworks, right? Just to have enough material to prepare for the exam, right? So, okay, that's it. I'm sorry I took longer than I expected a little bit, but check it out, all the algorithms, the problems, and let me know if you have any questions later, right?